Okay, so indexes with SQL Server. Let's start looking at them, hopefully understanding them some more, looking at the statistics that are built when you run queries against a database. So initially we've got our setup file here. So I provide this setup file. All it'll do is create this users table. You can ignore airports and nums. Airports was something I was going to hook up. Nums is something that helps us generate 1 million rows in the users table. So here we've got 1 million rows in the users table. There's a first name, a last name, an age, a last login date, something that I've called flight points. So it's, I don't know, points that you've earned, flying on a plane, and then current airport you could ignore because I haven't hooked that up yet. But there's 1 million rows in here in this table. So once you run the setup, you can close that because that will give you your database. I'm putting it in a database called Playground. Now you've got that data in there, let's start looking at indexes. So an index is something that we create that is like an index of a book. We can use it to jump to pages we are interested in instead of reading the whole book. So you don't really want to read a whole book if you can jump to an index, do you? And that's what indexes are with SQL. It helps you seek or jump to a point where you can then start reading the data. So, don't read the stuff you don't need to read the stuff you do need to read. So let's start with what we normally see when we look at a table. So let's run this. So if we look at the users table that we've generated, we can see under the indexes we have the PK user. So I'm talking here on the left when we open up users. If we look in indexes, we can see PK user, and it says it's clustered. When you see the word clustered, this means that it's the primary data set. So this contains all the column data. So all of this data, if I can select it, is the clustered index. So a non-clustered index is something we create from the clustered index. So we create it from looking at this. We have to read this to create a non-clustered index. These indexes are smaller than the clustered index as we specify fewer columns. There is no use creating a non-clustered index on a book with the whole book in the index. You want a subset, you just want an index for age or last name. So based on that, so you have one clustered index and can have many non-clustered indexes. So you can only have one of these. And in most cases, the clustered index is normally the ID or the GUID. If you don't have either of these, so if you don't have a clustered or a non-clustered index, then the table is known as a heap, which means, that should be which, oh, no it shouldn't, with no means of looking up data, and hence will always do a scan, be scanned from top to bottom. So if it's a heap without a clustered or a non-clustered, the only way you can read data is from top to bottom. So when we talk about indexes, we primarily mean non-clustered indexes. So we don't normally mean this table, we mean the non-clustered index, or I do anyway. When I talk about an index, remember it's the non-clustered index. So that's my personal definition. This is not a clustered index, but the ones that give us benefits later down the line are non-clustered index, when we see we need to increase performance. So when creating an index, the columns that you specify and the order of them for the index are important. Specificity should be the driving force when you are creating them. The more specific the data, the quicker we can jump to it, and the less logical reads will be done. So remember from my other session, a logical read is 8 kilobyte page. So one logical read is 8 kilobyte page. So let's turn on the execution plans. We can either do Control M, or we can click this icon up here. We'll make sure we're using the right database, which we are, but we'll run it. We've also set statistics on so we can see the details. When I say statistics here, these are statistics for the query running. We'll get onto other statistics that are used by SQL Server to have a better understanding of the data. So below is the query that we want to run. So this is our sample query. We want to know what users have 43 flight points and who have an age of 25. So give me a list of all the 25-year-olds that have 43 flight points, returning the user ID and the first name. Yeah. So if we highlight that and run it, we can see we get 152 rows back. You can see that it does a clustered index scan. So by this, if we click on the execution plan, we can zoom to fit. We can see it did a clustered index scan in the execution. So what it means, if we hover over it, it reads all 1 million rows in order to find 152 rows that match. So you can see this, which is the 6th column down, row even. Number of rows read is 1 million. So in order to find 152 rows, it had to read the whole table, and this is known as a scan. So it reads it top to bottom, and this uses, as I said, the clustered index. So PK user is PK user here. So it's done that. So if we now look at logical reads, you can see we get 12,225. CPU time 78. Which is actually matches for once, and the elapsed time 725 milliseconds. When I ran it previously, it was about a second. So it's taking a second to read 1 million rows, and those million rows are in the 12,225 logical reads, which is 8 kilobyte pages. So what I've told you above, let's create our first index. So looking at the query, which is up there, looking at the query, we can see that one of the two fields is age. So we can see we're looking for people who are age 25. So the other is flight points. So we're filtering on age and flight points. So let's first try and create an index on the age without investigating the data specificity. We're just going to add one on and see what happens. You would think, if you know anything about indexes, which you might not, is if we put an index on, normally it'll use it when it's in the where clause. So let's first try and visualize the index we want. This can be done with a simple select. So yeah, we're going to create an index on age, but we can visualize that by running this. So what we've done is we've done a select from the users, order by the age. So when we create an index, this one down here, it's going to look like that basically. It's going to be ordered by age, so everyone who's 24 is first, and as we scroll down, the ages will go 26, 27, all the way up to 40. So that's what our index will look like. So let's create the index. So create a non-clustered index, giving it a name on the users table with the age. And I like to use this because Brent Ozar mentioned it. It's maximum degrees of parallelism, which is set to 0, which means use all CPU cores to create the index. So we've now created our index. We can refresh here. There's our new index, and you see it's a non-clustered, whereas the primary one is a clustered. So in order to create this, it scanned this primary cluster and created a non-clustered index from that with just the age in it and the user ID. So let's run the query again. So we've run the query. So let's look at the logical reads. The logical reads are still the same. So what's happened? And the times are similar. Elapsed time's faster. I think that's just a hiccup in running it. So it hasn't actually improved performance. So why is that? If we look at the execution plan, it hasn't even used the index we've created. So what we see is that SQL Server decided that it wouldn't use the index. So why did it not use the index? If we run the following query, this one, we can see the statistics that SQL Server generated when we created the index ixage. So when we created this index, it also created a statistic. So what I mean is, if you open up this folder here, statistics, you'll see ixage. So you can see the statistic has generated for your table, which I've just said. So you can see it by opening this. You can't do anything with it. What you can do is run this command. And this statistics are histograms which are generated by SQL Server when we run a query on a column or columns. So we've run this query. Oh, these ones are automatic ones, sorry. I'll get onto those. And also when you create an index. Yeah. This is so that it has some understanding of the data. So these statistics are helping SQL Server understand the data. For example, it needs to know how much memory to allocate, and based on the number, also possibly different operations that you may need to perform. By operations, I mean if you look in an execution plan, you can see all the different operations, bitmaps and joins, all sorts of things. So the statistic that we're looking at here, or statistics in general, these views are 8 kilobyte files, so they can have 201 rows in them. What we see is that it created these statistics based on reading 1 million rows. Look at the row sample column. So here you can see that this statistic sampled 1 million rows. So if we look at the bottom table down here, it shows the range high key. So the range high key, which in this case is the age. So if you remember our data set, we had 24-year-olds to 40-year-olds. So that is with our index on the age, and this is how it sort of displays them. And then the EQ rows shows the number of matches for that age. So for 25-year-olds, it found 558,709. So it found 58,709 matches. So based on this, SQL Server now has decided that it would be more work to use the index, so ignored it and did a table scan. So even though we created our index, SQL Server had some intelligence to know you're asking for 25-year-olds. There's 58,709 of them. For me, I work out it'll be cheaper just to scan the whole clustered index instead of use your non-clustered index. So this is known as the tipping point, where SQL Server believed it would be quicker to just read the whole original table instead of using an index. So I'll run it again just so you can see, and then zoom to fit. So yeah, it will be quicker just to read the whole original table instead of using an index. So here it's read the whole original table instead of use our index, because there were 58,000, and it thought, might as well just read this. I don't want to do 58,000 lookups. So this is known as the tipping point. So what is the tipping point? There is no solid answer. So if I had more columns with bigger data fields, then it might decide to use the index. If the query is not using the index, then look at how many rows will be returned. This will be a good sign that you are not being specific enough. And again, this is around specificity. Asking for 58,000 rows isn't very specific. I've provided a link to Brent Ozar's I've provided a link to read a little bit more, and you can do extra research around tipping points if you want. But just because you have an index there, SQL Server has some intelligence to either use it or not use it. So if you have a clean database and you've never run a query, you won't see any statistics. There won't be anything in here. But as soon as you run a query, SQL Server will need some understanding of the data. This is where it will automatically create a statistic. You can see the ones generated by SQL Server named something like the below. So these two are automatically created. The important thing to note is the number 4 here, after all the zeros. This signifies that it's the statistic on the fourth column, which in this case is age. The WASys stands for Washington State System Generated Statistic. We can query it in the same way we did for the statistic we created when we created the index ixAge. So in this case, same command, same table, but we put the statistic name in there, the auto-generated one. And we can also actually, I'll show you the table again. So this is our table, and you see column 1, 2, 3, 4 is age. So that 4 is that column. So if we now run this, what do we see? You can see the rows sampled this time. So before it was 1,000,000 with our index, is not 1,000,000 this time. This because we didn't ask for an index to be created before we ran the query. SQL Server had no idea of the data. It quickly creates the statistic, but it only samples the data instead of look at all of it. As this will be faster, the data won't be as accurate as our index statistic, which will do a full scan of the original table to create the index. Hence why it makes sense to create a statistic at the time. So what I'm saying is, when you create an index, it has to scan every row in that table, so it might as well create the statistic at the same time, which is what it does. So the sample will be enough in many cases. So this sample of 109,000 will be enough in most cases to give SQL Server a good idea of the data it's working with. The data helps guide this, so this statistic or data in it helps guide SQL Server in estimating rows that will come back, and it can be a bit more intelligent when running your queries. So let's remove the index we created and then run the query just on age. Run this query, yes. So if you look at the execution plan and hover over the clustered index scan, you will see the number of rows per execution. So this is us using that statistic. We've got a statistic on that column. If I refresh this, get rid of the index, that other index, yeah, so now it's going to use this statistic to work out estimated number of rows. Okay, so if you look at the execution plan, zoom to fit, and hover over the clustered index scan, you will see the estimated number of rows per execution is 58,938.1. So yeah, we can see that that's 2, 4, 6, the seventh column from the bottom, 58938.1. This number comes from the statistics we just looked at. It's a good estimate based on the data it samples, which is good. So if we just run this command again, I'll get this and run this in another window so I can quickly pop between them. So if you remember, we asked, the query was where age is 25. I go back to the other tab. We've run this. If we look at the 25 row, we can see the number is 58938.09. So what it's done, that number is what you see here, but it rounds it up to, it's 0.09, 58938.1. Ours was 09, but it rounds it up to 1. So that's where that statistic or estimated number of rows are coming from, which is quite useful to know. So if you look at the execution plan and hover over the clustered index, yes, which we've done, shown you that. So now we have a bit of a look at statistics. Let's look at the specificity of our original query, which was this one. So now you sort of know when you run a query, you get a statistic. This helps SQL Server know how much data it's dealing with, and based on that, it can work out memory allocation. Should it use indexes? Should it scan the whole table? And in our case, the first example, it scanned the whole table because it knew there were 58,000 users, and that would be a lot of work, and it would be easier for it just to read the non-clustered the clustered index, this one. So this is our original query again, where the age is 25, flight points is 43. So we want to look at the specificity of this. So we can do this by counting the number of rows based on each parameter as follows. So let's run this one first. We work first, which we already know, but we'll run it for completeness. So when we run a count on the users where age is 25, we get 58,709 rows. That's quite a lot. So we want to be more specific in order to get better execution plans, better performance basically. Let's now do it on the flight points. So the flight points says we've got 2,521 rows, which is a lot less than 58,000 rows. Okay, so from this we can see that the flight points is more specific than the age. So for this particular set of parameters, we can see that if we create an index leading with flight points, then we will scan a lot less rows, and with any luck, SQL Server will decide to use the index because it will be below the tipping point that we saw above. So when we created it on age, it was above the tipping point and it didn't use the index. But here we're getting a lot less data. So with any luck, SQL Server will use this index. So let's create this index. We'll call it IX flight points on the users table, just with the flight points column with our max degree of parallelism on. So let's run that. That's run. Now let's run the query again and have a look at the logical reads. So our logical reads have now dropped to 7739, so something has changed. CPU time in my case is 15 and elapsed time is 106. They'll differ from these, as I always say. It's always a little bit different. But logical reads is consistently gone down. So this time, let's have a look at the execution plan. This time we see that SQL Server has used the index IX flight group. So here on this, just to the left of this, you can see now it's not using the PK user clustered index, it's using the index we just created, which is used, and this is used to seek to and then read 2,521 rows. It then did 2,521 lookups, and you can hover over these and you can see the second row down, 2,521. So it got the data here, then needed to do a lookup back to this clustered index, and returned the 152 rows to us. So remember, it does the lookup as the index we used didn't contain the age in this case. We also need the first name. So the age and first name were not in the index. Flight points and user ID were. User ID just comes in by default because that's the primary key for the table. So if the data we need is not in the table, then SQL Server needs to point back to the clustered index. So it points back to this one. I'll refresh this so you can see the index as well. And these. So this is known as a lookup. So this is it getting the rows, then it has to look up the age, and then also get the name if it needs, if it's a match. So remember, the clustered index has all the data. So this one contains all the data. So the lookup can get the extra data it needs. We can see that this has sped up the query quite a bit. So it was 12,000 logical reads, now it's going down to 7,000-ish. What we also see is a missing index recommendation. So Mr. Clippy, or the assistant built into SQL Server, Mr. Clippy came from Brent Ozar, like the Word document, Microsoft Word assistant, and it's telling you that you have a missing index as follows. So you can actually right click on the index and find index details, but I've just copied that out and pasted it here just to keep us in this file. So it wants us to create an index, whatever you want to call it, on age and then flight points, and also include first name. So this looks different than the index we have added so far. Why would you think this is? So when SQL Server recommends indexes, it will just do them in column order as they are defined in the table. In this case, this means the first column that it comes across is the age and then the flight points. even though we know that the index should lead with flight points instead of age. When we created an index on age, didn't use it, but when we create it on flight points, we can see it uses it. So just reread that again. SQL Server recommends indexes. It will just do them in column order as they are defined in the table. So what I mean by this is, let's do a select star. So the order it's recommending index on age, well, that's the first column that it's interested in, and then flight points. So it doesn't think all flight points first, it just looks in here and go, okay, the first column is age, so I'll put that in, the second column is flight points. So it says you need an index on age and flight points, but in actual fact we need an index on flight points and possibly age, which we'll see shortly. So that's something to bear in mind, that don't believe what it tells you, use what we've done around specificity. So this may surprise you and show that you should never just create the index it recommends. Instead, you should do what we have already done and look at the specificity of the columns. You remember when we did the counts here, we found that this was more specific. So that's a sign that this should be the leading column in the index. Where did we get to? Instead, you should do what we've already done. Yep. Also, be very careful of adding all the columns that it recommends. Very often it can be asking for a large index with all the columns in it, which defeats the purpose of the index. You only really want columns that are below 200 characters, so all your normal ones, ints and dates, are fine, but anything over a varchar 200 in index is a bit of a bad smell. You shouldn't start doing that really. So yeah, let's continue where we left off. So we can make this query even better by adding the age to the non-clustered index. So let's do that next, but let's first drop the index we created. So we've currently got it down to 7,739 logical reads. Let's drop that, what we've created. So now let's visualize the index again. So like before, we're going to do select flight points, then age, and then user. From DBO user, and then order by the flight points and age. So this is the index. The index is going to be on flight points and then age. So if we run this, oh, wrong button. So if you now imagine a request, so we've got our index. We haven't got our index yet. No, we will afterwards. This is just me explaining it. So yeah, so if you now imagine a request comes in for flight points. So imagine we've got our index. This is it here below. And they are looking for flight points 1 and age 25. So you will skip all the rows that don't start with 1 from flight points for flight points. So we're going to skip all of these. We have no interest in them. They're all 0. We want to start at 1. So I'm just scrolling. I think it's about 1,000 something. There we go. There's 1,000. There we go. So here you go. You will skip all the rows that don't start with 1 for the flight point. So we've skipped 1,277 rows. We've not read them. Then skip all the rows that aren't age 25. So we're currently at age 24. So we need to skip all of the 24s. And to here. Now we read all the rows that match this criteria. So all of these, we read them all. So let's scroll all the way to the bottom, or not to the bottom, to 26. So from line 1403, we read all the way to, oh, gone too far, here, 1533. So we don't read many rows, so we read all the rows that match this criteria. At this point, we're not interested. Now we're on 26. What we do is we return. We don't need to read the rest of the million rows. So this is, as I've said, when we hit the end of this range of data, we return, not reading to the end of the table, like a table scan might do. So this is known as a seek. As we didn't scan the index from top to bottom, we seeked or jumped to a point to start reading the rows. We read all the rows that were a match, and then we returned. So we read a lot less data, basically. So you only read the rows you actually want and then return immediately without scanning the whole table, which is what happens when you don't have an appropriate index in place. So let's create this index. Now we visualized it. Let's create it. Let's run the query again. Let's look at the messages. Let's look at the logical reads. So the logical reads are now gone down to 477. Previously this was 7,700 and something. CPU time is now 0. Elapsed time 103. I got it 70 before. So this time it does quite a few less logical reads. It still had to do the lookup on the 152 items. So let's have a look at the execution plan. So this time, if we hover over it, the sixth column down says number of rows read 152. So we read exactly the right number of rows. We read no more and no less. Those 152 rows are returned, and then we do 152 lookups. So this time we do quite a few less. Yeah, it still had to do the lookups. This is because the index doesn't include the first name, which we need in the final output. So we've included the flight points and age, but our query is also asking for the first name. So I'm going, so I did want to mention which needed the flight outputs. Here. So the second bold output list near the bottom, you can actually see what it's looking for. It says first name, so the second bold one, first name. So it's trying to pull that back. That's why it's doing the lookup. If we didn't need the first name, you wouldn't get this lookup. So that's not bad. Lookups like this are fine, not inexpensive, and a good solution. So let's squeeze every ounce out of this. Let's create a covering index to get it as fast as possible. Note that we don't normally want to do a covering index, as this makes it specific to your query. We generally want to make indexes usable by other queries. Quite often, 1 or even 2 columns is enough in an index, as we don't mind doing lookups when it's below a few thousand rows. Remember, based on Brent Ozar's rule of thumb, that a table should have a maximum of 5 indexes with a maximum of 5 columns and 5 includes. You can go over this number, but remember that the more indexes you have, it will also affect write speed. If the index contains a column that is being changed, that index will also need updating. So in the case of, I don't know, I have 5 indexes in here, and I've got the first name in every one of them. If I do an update of the first name, that will go into the clustered one, you know, the one that controls all the data. But all indexes that have the first name in it will also need updating. So if I have them in 5 indexes, I'll have to write to this table, and I'll have to write to the 5 indexes as well. So these are things you have to weigh up, but that's why 5 and 5 isn't too bad. You know, if you've got loads of indexes, then you've most probably got write issues, depending on if that column's in there. So let's drop the index. Oh yes, because we're going to create a covering index now. So let's drop the index. So let's visualize this index again like we did. So we've got our order by flight points. So it's exactly the same as before, except this time we've got the first name in there. We've included the first name. So if you need user, 24, we don't have to do the lookup because we've got the first name in here. So that's visualizing it. Note, not much has changed. Yeah, we just included the first name into it. We also include, we add includes normally when we need the data in the result set, but it's not required in the filters such as the where clause. So first name isn't used in the filters. These are like filter clause, these don't need to be includes, these need to be in the top part, but things that you just use in the select, these can be includes. So we're going to create the index. Let's create the index. Okay, that's created. Let's run the query again. Showing, Logical reads has now gone down to 5. We can look at the CPU. CPU was 0 before, it's still 0, and milliseconds is still about the same. But we've gone from scanning the whole table, which is doing 12,000 logical reads, down to 7,000 logical reads, down to 400 logical reads, and now we're down to 5 logical reads, and this is with a covering index. But as I say, we shouldn't really do covering indexes because they're very specific to a query. But if you needed to squeeze every ounce out of this, this would be the optimum index to actually fulfill this query. So you will now see that the lookup has gone. Yeah, let's look at the execution plan. So before we had a lookup, and we get even less logical reads. So yeah, it read 152 rows, returned them, had everything it needed. I didn't have to do lookups for the full name because it was included in this index, and was really fast. You may be asking the question, how come we don't add the user ID to the index? So in here, in our example, we said show the user ID, but we didn't add that user ID here, but we didn't add that to the index here. IX, flight points, age, first name. So why didn't we add the user ID? Well, when SQL Server creates an index, it actually stores the primary key under the hood. You should realize that in order to do lookups like we were doing, it needs the key to find the row and read the extra column data from the clustered index, which may not be in the clustered index. Okay, so a common thing I see is that people specify the primary key in the index, which in actual fact you don't need to declare it. It will be available nonetheless. SQL Server uses this as a pointer in the case it needs to do a lookup. So note for the future, don't add the primary key column to the index because it'll be there anyway. Hence why I've not added user ID in here, because it's the primary key. SQL Server will automatically add it to this index so that we can do things like lookups to get, the last name or some other field that we don't have in this index. So let's clean up that index. So we should have no indexes again. So we'll move on to a bit more maths, which might be scary for you, but I actually lay out the formula, so you could run this yourself, have a play with it and see what you think. So how are estimated number of rows worked out? So let's go back to the statistics that were initially created for us. I will show you how the estimated rows is worked out for our query. Remember, this is the automatically created one. Yeah, remember this is the automatically created one as we have now removed our indexes. So yeah, if we back look in statistics again, refresh, we're going to be talking about these two. So these are the statistics on column 4, which was the age, and column 6, which is the flight points. Okay, so I'll just reread that again. So I'll show you how the estimated rows is worked out for your query. Remember, this is the automatically created ones, as we have now removed our index. So the original query for reference was this one, where we're getting age is 25, flight points is 43. We remove the indexes so it's back to normal, but we want to understand, if we hover over this, zoom to fit, where does estimated number of rows come from? So that is the 7th column from the bottom. Estimated number of rows per execution, 635.997. We want to figure out how is it working out or estimating that it needs 635. It estimates there'll be 635 rows that come back. That isn't what comes back. We get 152, but that's fine. If you're, according to Brentoza, if this is like 10x off, then you might have issues. But that's a good estimate. It's better to overestimate than underestimate. It'll give it, if it needs memory allocation and things like that. But we just want to work out, where's this number coming from? How are we working out that 600 and 35.997 rows will come back. So let's look at the statistics on the age first. So if we run this, so for age 25, this row, EQ rows is 58938.09. So what we do is we get that value, we copy that, put it here, we divide it by 1,000,000 because that's how many rows are in here. There's your rows, so we divide that by that. I'll drag this up a bit. We get this number here, 0.0589. That is the age column done. Then we look at the flight points column. So because flight points was for 33, so let's have a look down here for 33, 43 even. So there isn't 43, there's 41 and 44. So if you remember, I said there can only be 201 rows in here. I think there's 200 in here. You can't have any more, so it has to sort of partition them, or so there's 42 and 43 before this range in here, and this is where we're going to use the average range rows. So as I say, it was 43. It's currently between 41 and 44 in the statistics. So we take the average range rows column of the range high key 44 for the calculation. So because it's between 41 and 44, we take the 44 row, we look along right, and we get the average range rows, which is 2619.733. So that's our value. We then again divide that by 1,000,000, and we get this value here. So remember, our flights points was the most specific thing, so this number is smaller. And this number is bigger. Just bear that in mind as we go through this. So the smaller one is more specific. The formula is as follows. So starting with the most specific value, which is this one. So the flight points, because we could seek in quicker, we start with that number. So we put that there. Starting with the most specific, this is the smallest number. We then multiply this by the square root of the second value. So this was the age. So range rows multiplied by the squared root of the age, and then we multiply it by 1,000,000, and what we get is 635.996. This is me just doing that calculation. The square root of that is that. So this is where we get that value. So if I just copy this and run this in here, and then we need execution plans, and then so if I hover over that, you remember we get 635 just on the right there, 635.997. So that's the estimate. If we look at the numbers, 635.996. So what it's done is it's rounded up that 9 to a 7, and that's where we get the estimated number of rows. So if we hover over the query, we can see the estimated number of rows is the same number, 635 in this case, which is just done here. It says 636 here, but I'm looking at this one here, 635.997, so it's rounded that one up as well. That's where the estimated rows have come from. So if you had a third column, you would have the third value with 2 square roots. So in this case, if we had a third column that was less specific, it would be that, the square root of the square root of the number multiplied by that. But remember, your most specific one is the first one, and then as they decrease, less specific. And this can go on for quite a bit. So little bit of interesting how these estimated number of rows are worked out. I believe it did change. The cardinality estimator changes, so these values may change in the future if they change it, but this is the current one that works in 2017 and 19. Also note that the values in the multiplication are ordered by specificity, which I've said. The one which will be the most specific will be the first, and then subsequent ones in less specific order will be after. So most specific is the smaller number, remember, flight points, and then that one's a bigger number, so that was the age. Okay, in our case, the flight points was more specific than the age. So I've taken you quite a lot. We've looked at indexes, we've looked at statistics that are used to help SQL Server understand the amount of data. If there's too much data, it will actually not use your index and it might decide to scan the whole table. So I've taken you through specificity. So try and find the columns that are the most specific for your query and lead with that to create your indexes. And in summary, yeah, heaps, I mentioned heaps. So there's no index at all, and it has to read to the bottom, has to read top to bottom. See, I'm still correcting this. Yeah, so heaps, they don't have an index. There's no clustered or non-clustered. And if you have a heap, it's normally a bad sign. You need at least a clustered index on that. Has to read top to bottom. But if it's got a few rows, then maybe it's all right. You know, you don't mind reading 100 rows. But if it's got thousands or tens of thousands, then you most probably need a clustered index, and then most probably non-clustered indexes for your queries. So yeah, heaps are sort of bad. Remove them. Not remove them. Turn them into clustered indexes. Okay, so we talked about clustered, so there's only ever one, normally not a number or a GUID, as we saw in the user table. Like this one, that's the clustered index, which in our case is a number, but I've seen people use GUIDs as well, but I prefer numbers. So non-clustered, so the ones we create to make queries faster. So this is what we've worked through above. We've created 2 or 3 different versions to make our queries faster and faster based on logical reads. Specificity is key, so being specific, finding, as we did, we found the more specific data set, which was flight points and not age. Age wasn't specific enough, and that's why SQL Server didn't use the index, and hence it scanned the whole table. I've shown you statistics and the histogram that helps you visualize the data distribution. And then finally, bit of maths, which might be complex, but I'd say give it a go, have a play, and then it will make it more understandable that how are estimated rows calculated. As always, quite a lot to take in, but happy to answer any questions. But yeah, so we've gone basically from 12,000 logical reads to 7,000 logical reads. There we go. Then we went from 7,000 down to 447, that one, 477. And finally, we did a covering index, which gave us 5 logical reads. But I'd stay clear of full covering index unless it's absolutely necessary. 477 logical reads is perfectly fine, and you could happily leave it there. You can overdo it, and then other things may not actually use your index. So that's it. Thank you for tuning in. I hope it was useful. I'll see you guys later. Cheers.